start. Okay, so good afternoon. So today we are going to discuss light sterile neutrinos. So the topic has already been addressed by Gabriela yesterday. So I will try not to repeat what she said. So I will basically present the formalism, which is not very complicated, but might be useful for those of you who have never seen it. So how light sterile neutrinos affect neutrino oscillation probabilities. And then I will show, which was mentioned by Gabriela, but one can show it very simply, how different experiments contradict each other. And even if you take seriously the anomalies like LSND mini-boon that Gabriela told us that we should take with a grain of salt, and I agree, even if you take them seriously, the data from all experiments is not consistent with an explanation in terms of light sterile neutrinos. So I will try probably to be quick on this part. Then we will move on to heavy neutral leptons. So heavy neutral leptons are just sterile neutrinos in the GV to TV range, and they are possible remnants of the mechanism of neutrino mass generation. So we want to see if we can access them at experiments. And finally, if time permits, I will discuss leptogenesis, and in particular low-scale leptogenesis, where we will see that also these heavy neutral leptons could play a role there. So everything will be somehow connected. Okay, so let me start with sterile neutrinos. So as is well known, so and as well said also by Gabriela, so we know from LEP that there are only 3 active neutrinos, meaning active meaning coupling to the W and Z bosons. This is from the measurement of the invisible decay width of the Z boson at LEP. But we could have additional neutrino species that have no weak interactions, the so-called sterile neutrinos. And in that case, they would only interact through their mixing with the active neutrinos. So the active neutrinos are the ones that we know, nu, nu tau, and that have electric interactions. And they would affect their oscillations. So as I said, they have been invoked in particular to explain some experimental anomalies, but as also Gabriela pointed out, they could exist even independently of these anomalies. So a more theoretical motivation maybe is that they are there in many models of neutrino mass generations, which often involve right-handed neutrinos. If we consider, for instance, the CISO limit, the sterile neutrinos, we have seen that yesterday, are very heavy, and they mix very weakly with the standard model neutrinos. So this will have no impact on oscillations. But in general, there is no reason to assume that they're extremely heavy, so they could be down to the electroweak scale or even below. But there is a general prediction of the CISO mechanism as long as MD is smaller, the Dirac mass is smaller than the mass M. The generic prediction is that the active neutrino mass is given, this is a 1 generation estimate. It's true actually, it's an estimate, but it's true in the case of 1 generation. The active neutrino masses are given by MD squared over M. And the mixing angle between the active and sterile neutrino is given by MD over big M, which means that you can re-express the mixing angle as being the square root of the standard model neutrino mass divided by the sterile neutrino masses. So from that, you immediately get that the lighter the sterile neutrino, the stronger they're mixing with the active ones. And in that case, they can have some impact on their oscillations. While if they are very heavy, this mixing angle is going to be very small. So this is a useful relation that one should keep in mind. So what about active sterile neutrino mixing? This is just the theoretical framework, which again is very simple. So the standard case is that one that we know very well. We have 3 active neutrinos, E mu tau, and nu1, nu2, nu3, 3 mass eigenset, and they mix with the entries of the PMNS matrix. Now, if we add a sterile neutrino, now we have 4 mass eigenstates. So let me call nu4 the 4th one, and its mass m4. And we have also now the sterile flavor eigenset, the one that doesn't couple to the Z and W boson, that I will call nu-S. And we again have a PMNS matrix with this relation that is now a 4 times 4 unitary matrix. So we sum over 4 mass eigensets, and alpha can take also the sterile value S. Now we know that only nu tau coupled to the electric gauge bosons, but they can be produced in weak processes because the nu is going to be a current superposition of all four mass eigensets. They can be produced provided, of course, that this is kinematically allowed, that the nu for mass is smaller than the energy available in the decay. Okay, so what if now we are talking about four flavor oscillations. So we have new oscillation parameters in addition to the 2 delta m squared that we usually have. We have delta m squared for 3, for 2, and for 1. We have also 3 new mixing angles, theta 1, 4, theta 2, 4, theta 3, 4. Or if you want, you can treat them with the entries of the PMS matrix that involve the fourth neutrino mass, UE4, UMU4, U tau 4. So now I'm going to consider a very simple limit, which is adapted actually to these experimental anomalies. I will consider short baseline oscillations. First of all, I assume that M4 is heavier, let's say in the EV range or a bit above, such that delta M square for 1 is larger than delta M square 3, 1, much larger than delta M square 3, 1. And I am in experimental conditions such that the argument of the sign in the oscillation formula, delta M square for 1 L over 4E is of order 1 or smaller. In that case, what I can say is that this oscillation factor, sin square delta M square for 1 L over 4E, is going to be much larger than the one corresponding to atmospheric and solar neutrino oscillation, let's say, the delta M square 3 1 and delta M square 2 1. So I can describe things by doing a simple approximation. Since this is small, I just neglect this delta M squared. I set them to 0, okay? Because I'm interested now in a regime where it's mainly this delta M squared that is going to drive the oscillations. And then if I assume that all 3 new delta M squared are equal to each other, okay? So I will just keep delta M squared for 1. Then the oscillation probabilities, which are in principle complicated because I have now 4 flavors, they reduce to very simple expressions. So let me start with the disappearance probability, and then I will discuss the appearance probability. So the disappearance probability is the probability for nu alpha to be detected as a nu alpha. It's just given by this very simple expression. Of course, I have made those assumptions. And using the unitarity of the 4 times 4 PNS matrix, I can write it in the form of something that looks like a 2 flavor oscillation, where here this sin squared 2 theta alpha alpha is simply defined by this. This is 4 times 1 minus u alpha 4 squared times u alpha 4 squared. Very simple, okay? It's the effective mixing angle that governs short baseline disappearance. Now this is the appearance formula. I produce a nu alpha, and in my detector, I want to see nu beta. So what is the probability? Again, I'm using the unitarity of the PNS matrix, and I express it as a 2 flavor, something that looks like a 2 flavor oscillation formula with an effective mixing angle sin squared 2 theta alpha beta that is just 4 u alpha 4 u beta 4 squared. Okay, with of course the mixing with the 2 flavor alpha beta that are involved in the appearance. Now, excellent status of anomalies. This has been covered by Gabriela, so I will just refresh your mind and not go into the details. So there was a reactor anomaly due to a re-evaluation in 2011 of the predicted neutrino flux from reactors, and it was found to be smaller than previously thought. So the conclusion was that, to be larger. The conclusion was that actually in reactor neutrino experiments, we have seen short baseline reactor neutrino experiment, we have seen a deficit. And then how do we explain this deficit? We can explain it by short baseline oscillations. For this, we need a new delta m squared. So let's invoke a sterile neutrino with a delta m squared for 1 of order 1 ev squared and mixing angle sin squared 2 theta e of order 0.1. Okay, I'm saying this is now, I mean, the question is clarified, but just to summarize the value of the parameters that were needed to explain this. Okay. Then there was the gallium anomaly, again, coming from the calibration of the GALEX and SEJ experiment, with radioactive sources that produce NUI. There was a 3 sigma deficit. Actually, it has been confirmed by the best experiment, which again can be understood in terms of sterile neutrino, light sterile neutrino, with the delta m squared for 1 for the 1 ev squared, sin squared 2 theta e for the 0.1. So more or less consistent with the reactor antineutrino anomaly, and the region in the UE4 squared delta m squared for 1 parameter space is given by this red region. So in fact, as Gabriela told us yesterday, there's been a revelation of by different methods of the prediction of the neutrino flux, antineutrino flux from reactors, and the conclusion is that the significance of the reactor antineutrino anomaly decreases to 1 sigma or so, meaning that there is actually no anomaly. This is just short baseline experiments that have been designed after the reactor antineutrino anomaly to look for those short baseline oscillations, and basically they have produced negative results and excluding most of the region allowed by the reactor antineutrino anomaly. I'm just flashing that without commenting more, since this is a negative result. And this is the update on the gallium anomaly from the best experiment, which has confirmed deficit and with an increased statistical significance. So Gabriela has an updated significance of 5 sigma yesterday. However, this one requires an even larger mixing angle. Again, you can explain it in terms of light sterile neutrinos, but you need an even larger mixing angle that is in conflict, basically, with solar neutrino data and also other experiments. So the situation is very confusing, to say the least. Now, I was talking about disappearance experiment. Okay, it was a NUI or NUI bar deficit in NUI bar neutrinos. Now, short baseline appearance experiment. So, namely the appearance of a nu mu in a of a NUI in a nu mu beam, or a NUI bar in a nu mu bar beam. And again, this was discussed by Gabriela. So there is this LSND experiment, the mini Boone experiment that was designed to test it, first delivered inconclusive or contradictory results with some excess found in neutrinos and not in antineutrinos, or the opposite, I don't remember. And finally, with the full set of data, they found low energy excess, which they could fit together with LSND. So Gabriel told us what we should think of this fit, but in any case, if you do that fit, you find that you can accommodate the two anomalies with sterile neutrino in the EV range, so delta m squared for 1 or for the 0.1 EV squared, and now a small mixing angle, because larger values are excluded by other experiments, between 10 to the minus 3 and 10 to the minus 2. So now this is this effective mixing angle that governs short baseline appearance. So do not confuse with sin squared 2 theta e previously. This is sin squared 2 theta mu e. However, it turns out, so those parameters in principle could accommodate the LSND and mini Boone excesses. However, it turns out that we also have other disappearance experiments, this time in the nu mu sector, coming either from long baseline oscillation experiment, this is the MINOS experiment, or from neutrino telescope, which observe atmospheric neutrino, namely the ice cube experiment. So to make a long story short, there is a conflict between the appearance data, LSND and mini Boone, which gives this allowed region in this parameter space, and disappearance data, so essentially MINOS and ice cube plus some other experiments. Rather than commenting this plot, let me try to explain in simple terms with the simple formula that we have written why there is a contradiction between those different experiments. What is the origin of the conflict between the appearance data from LSND and mini Boone and the disappearance experiments? So the reactor ones for the NUI sector and accelerator or ice cube for the nu mu sector. So remember that in the reactor we have disappearance control by this formula, where sin squared 2 theta e is basically you can approximate by 4 UE4 squared. Okay. In minus ice cube, so nu mu disappearance, this is controlled by sin squared 2 theta mu mu, which is basically 4 U mu 4 squared. And finally, the appearance experiment, the nu mu to nu e appearance probability is given by this formula, where sin squared 2 theta mu e is of the order of 4 UE 4 squared times U mu 4 squared. So now it's very simple mathematics to show that there is a relation between these, an approximate relation between these mixing angle, that sin squared 2 theta mu e is roughly 1/4 sin squared 2 theta e times sin squared 2 theta mu mu. Now you have a problem. You want the sin squared 2 theta mu mu to be small, but not that small, in fact, while nu mu disappearance experiment tells you that the sin squared 2 theta mu should be small. And even if you, so now even if you believe in the gallium anomaly, sin squared 2 theta e is let's say 0.1, 0.2. It's not 1. So you have here a left-hand side that you want to be rather large, let's say. I said it was small, but rather large compared to right-hand side, which is small. And this is shown in this plot by these people, where you have sin squared 2 theta mu e, the appearance mixing angle, on the x-axis. On y-axis, this is the delta m square for 1. And in red, you have the region allowed by appearance data. And here in blue, this is the exclusion. The excluded region is to the right of this blue curve from these appearance experiments. So the conclusion, and basically is the one that Gabriela told us yesterday, is that even if these anomalies are real, they cannot be explained by light sterile neutrino. And actually, things do not improve if you add more sterile neutrinos. One could ask the question. It doesn't improve the situation. So if these anomalies are real, they must have a new explanation, unknown backgrounds, or some other kind of new physics. This plot I will not comment because I'm not an expert. It's just to say that sterile neutrinos, which mix strongly with active neutrinos in the EV range, are in conflict with cosmology. Yes? To quantify it, I don't know by Earth, but I think it doesn't, if I remember correctly, it doesn't improve the situation. I mean, you still have, the formulas will be, of course, more complicated. You don't have these simple formulas that I presented, but you still have this tension. I'm not able to give you a number of sigma if you can find, for instance, but this is just also be studied in papers. I don't have a reference in mind now, but you can look at this talk, for instance. So it's, and two sterile neutrinos would be even more in tension with cosmology, namely with the effective number of relativistic species. I do not discuss that because Yvonne is much more expert than me. So yeah, so basically the conclusion is that, first of all, there are, I should mention that, there is a short baseline accelerator neutrino program at Fermilab called SBN, which will again test those anomalies. And it consists of 3 reactors. There is a near reactor, there is microboon that Gabriela mentioned yesterday, and a far detector, which is Icarus. So EV scale sterile neutrinos do not seem to be around, but sterile neutrinos might still be present. And now I'm going to move on to heavier sterile neutrinos, which have nothing to do with those anomalies and that are not yet excluded, namely in the GV-TV range. So the so-called heavy neutral leptons. So I'm interested here in the potential signatures of low-scale neutrino mass generation. So basically, I think I said this on my first slide. From the a mechanism like the type 2 CISO, we don't know we don't have a prediction for the scale of the sterile neutrinos. And if they are around electroweak or TV scale, they can be produced at colliders through their mixing with the standard neutrinos and constrained by many other experiments, which I'm going to discuss now. So it's just an introduction. So again, heavy neutral leptons is a generic name for sterile neutrino in the GeV to TeV range, which could be produced at colliders and which are possible remnants of the neutrino mass generation mechanism. So the fact that they are sterile means that they only interact through their mixings with the active neutrinos. And due to their mixing with active neutrinos, they will acquire effective couplings to the W and Z boson. So this is the Lagrangian that we're going to focus on. I consider a single heavy neutral lepton. And U alpha n is just an entry of the PNS matrix. So previously we were calling it U alpha 4. It's the active sterile neutrino mixing. So there are actually 3 entries here because alpha is E, mu, or tau. And you see that normally the W would couple a charged lepton of flavor alpha to a light neutrino of flavor alpha. But since the light neutrino of flavor alpha mixes with N, the heavy neutral leptons, with mixing that is U alpha N, you get this vertex here between the W charged lepton and heavy neutral lepton, which is weighted by U alpha N. And the same for the Z. So the Z couples a nu alpha to an anti-nu alpha. So now you can have, due to mixing, an anti-nu alpha coupling to N with a weight which is U alpha N. Again, this active sterile neutrino mixing. So what does this mean? This means that these heavy neutral leptons, we can produce them in W or Z decays or via off-shell W or Z boson if the sterile neutrino is heavier than the W and the Z. Not only we produce them through these couplings here, but also their decays are mediated again by on-shell or off-shell, depending on the sterile neutrino mass, W and Z boson. Consider, for instance, the decay that goes for a W boson, where this one can be, again, on-shell or off-shell. So N, just for this Lagrangian, can decay to LW, and W can decay to jets. So this will give you a charged lepton decay of the sterile neutrino into charged lepton plus 2 jets, or it can decay leptonically, in which case you will get 2 opposite sign charged leptons plus a neutrino. If the decay goes through the Z boson, so the N decays to nu Z, and Z can decay to jets, to charged leptons, or to neutrinos, which would be completely visible decay of the heavy neutral lepton. And the important thing to remember is that both in the production of the heavy neutral lepton and in the decay, there are these effective couplings. So both of them are suppressed by U alpha N squared, by the active sterile mixing angles. The production cross-section is proportional to U alpha N squared. Well, in principle, you need to sum over different flavors, but I'm simplifying. And the decay rates also are suppressed by U alpha N squared. So in principle, by doing different experiments, searching for these objects, these heavy neutral leptons, one can constrain, one can constrain the active, now I think I have a problem on the next slide. One can constrain the active mixing sterile, the active sterile mixing angles as a function of the sterile neutrino mass. It seems that I have a problem here that one does not see the plot. Yes. Did you use Acrobat Reader or? Well, there should be a plot here. So maybe, do you have a different PDF viewer than Acrobat? So I think this was around 20, slide 20, something like that. Okay, let's use that one. I never understood. PDF means portable um, document format, and in fact, it's not portable as you can see. Depending on the PDF viewer that you use, you don't see the same thing. Can we go now? Maybe there's a surprise when we go to full screen. It might be that the plot disappears again. If we cannot go to full screen, I can also use that, but we're not in Acrobat, so maybe it's different. Thanks a lot. Okay. Thanks a lot. Okay, now, oof, because I wanted to spend a lot of time on this. So this is a nice plot. It's a bit old, so it's not completely up to date, but it's nice. That's the reason why I'm showing it, and it's better to discuss it. So the warning is that indeed it's a bit old, so the LHC constraints are not up to date. I will show then an updated plot. And some future experiments are missing, and you may wonder what LBNE here means. It's obsolete. It was the former name of Dune. So that's for the Dune near detector here. So what you see here are the constraints on the UEN squared, UEN squared. So it's the mixing of the sterile neutrino with the electron flavor as a function of the sterile neutrino mass. Now I'm going to describe the various constraints that you have. First of all, here there is, you see a BBN constraint. What is it? It's just to the fact that Big Bang nucleosynthesis basically doesn't like new species that decay within 1 second or so, because they will spoil the prediction of, they will destroy basically the light elements that have been produced by BBN, and they will spoil the prediction of BBN, which we know are successful. So this is from requiring that the sterile neutrino has a lifetime which is larger than 1 second or so. Here you have a limit. So as I said, it needs to be updated. So Gerda at that time had the best limit on neutrinoless double beta decay. Now it's Camlan Z, but since we're on a logarithmic scale, that wouldn't change anything, in fact. So where does this limit come from? So it comes from the fact that while light neutrinos contribute to the neutrinos double beta decay amplitude as sum over I mi UEI squared, in the case of heavy neutrinos with mass larger than 100 MeV, typical momentum of the nucleon inside the nucleus, yes. The amplitude is proportional to, of course, it's the mixing with the electron flavor, UEN squared divided by Mn. And if you incorporate that constraint, it gives you that, that limit, meaning that everything that is above this is excluded. So this limit tells you there is an uncertainty due to the uncertainty of the nuclear matrix elements, but it tells you that everything that is above this limit is in principle excluded, which is not a good news because we want to explore this region. But in fact, there's a way out. So there can be always cancellations in the neutrino double beta decay amplitude, either due to Majorana phases, which are not taken into account in this limit, or to the neutrino mass mechanism itself. And I'm going to comment about that later. This is the case of the so-called inverse ISO mechanism. So this limit is actually model dependent. One should not take it at face value. So now let us comment on the other experimental constraint. You have constraints like here this P2E nu or K2E nu, which are due to peak searches in leptonic meson decays. K can decay, K-on can decay to a charge K-on to an electron and neutrino. So it means that it can also decay to, in that case, a positron and a sterile neutrino. But that rate will be suppressed relative to that one by UEN squared. But the nice thing is that since this guy is massive, there will be a shift in the electron momentum due to the mass of the sterile neutrino, so that will result in a peak. that is easy to see, sorry. And there are also constraints from semi-leptonic B meson decays from Bell or muon and tau decays from B factories. And basically this is, so I was commenting about that and that. Now this is another semi-leptonic decay. And here there is a constraint from Bell, for instance. Another type of constraint comes from bin dump experiments. In that case, you search for the decay products of the cell neutrino that are themselves produced in semi-leptonic meson decay, and then they will decay back to jets and charged leptons. You have here the limits from previous experiments, so like this PSI, PS191, CHARM, NF3, etc. And there is a planned experiment at CERN which is called SHIP, that one here, which again is a beam dump experiment. And if it is done, it will strongly improve the constraint on UEN squared. There are also constraints from lepton number violating meson decays, because the AV neutral lepton is Majorana fermion in principle. So a meson can decay to n plus other things, and the n can decay, giving, for instance, two charged leptons of the same sign. Okay, and this is the constraint indicated as Bell here. I didn't comment this. This is the brown dashed line here is from electroweak precision observables. And finally, let me now come to, okay, so sorry, before coming to collider searches, I haven't commented yet L3, Delphi, Atlas, CMS, and FCCE. I'm going to do that soon. So now those are the same constraints for the mixing to the muon flavors. So there is no longer the Neutrinos double beta decay. And this is for the mixing with the tau flavor, where there are much less constraints for various reasons, especially the fact that the tau lepton can decay hadronically, so it's not it's much more complicated to reconstruct. So before coming to collider searches, let me make a comment. I didn't say anything so far about this CISO line here. So let me now comment about that. Previously, we have seen that the active sterile mixing angle squared is given by the ratio of the standard neutrino mass divided by the sterile neutrino mass. And in fact, this constraint E tells you that if you are above this CISO line, basically the value of the mixing angle is such that the neutrino masses, the standard neutrino masses, would be much higher than what they actually are, because basically you violate this bound. So everything that is above this line corresponds to U alpha n squared much larger than this ratio. So it seems that the parameter space that is accessible to experiment is excluded by neutrino masses. In fact, it's not completely true, because this is strictly speaking valid in the type 1 CISO and valid for one generation. So in practice, it's a bit more complicated, and there are alternatives or variations of the type 1 CISO that allows you to have an active sterile mixing angle that violates this relation, that is much larger than this ratio. And an example of this is the so-called inverse CISO mechanism that I'm going to introduce now. What is the inverse CISO mechanism? Well, instead of adding a right neutrino for each generation to the standard model, you add two sterile neutrinos per generation with opposite chiralities, so NR and SL. They both are leptons, so they both have lepton number +1. And now the CISO mass matrix, which was 2 pi 2 previously, I'm working again in the one generation case, is now 3 by 3. And you see that you still have, as previously, the Dirac mass here from the mixing between the standard neutrinos and N. You have here, big M now is, sorry, there is something wrong here. So big M corresponds to the off-diagonal mass term S bar N. Sorry, this is completely wrong. This should be big M S bar N. And finally, there is a new mass scale, which is mu, and mu corresponds to S bar S. Sorry, not to what is written here. Mu corresponds to S bar S. Now, if you, actually it's SC bar S. It's a Majorana mass term for S. Mu is a Majorana mass term for S, and M, if you want, is a Dirac mass term because nu R and SL have opposite chiralities. So what does it mean? It means that both MD and big M are Dirac masses. They do not violate lepton number. And this mu here is a Majorana mass. It is the one that violates lepton number. And the result of that is that now the large neutrino masses are controlled not by MD over big M, but by this small lepton number violating mass mu, which is again not S bar N. It's the Majorana mass for S. And the large neutrino masses are given in the one generation case by this formula. So you have basically MD squared over, well, it's written as matrix, so it's not one generation, but let's say it's MD squared over M squared times mu. So even if MD, remember that MD over M is a mixing angle, active sterile mixing angle. So even if it's not that small, we can make the Sandwell neutrino masses small by lowering the scale mu, the lepton number violating scale mu. So that's the conclusion. We can have large active sterile mixing angles with heavy neutral leptons in the GVTV range, provided that mu is much smaller than M. And just a small comment, in that limit, S and N actually form a what is called a pseudo-Dirac term. Just a comment for people who know what this means. Okay, so that's a way out to avoid being killed by this neutrino mass constraint here. So let me now move on to heavy neutral lepton collider searches. And let me start by E plus E minus colliders. So historically by LEPT. So at LEPT, you could produce heavy neutral leptons via a Z boson. E plus E minus goes to Z off shell or on shell, so off shell at LEPT2, which then gives heavy neutral lepton plus a sound model neutrino. And there are limits in the previous plot that I show you for all neutrino flavors from Delphi that are of the order of 10 to the minus 5 on the mixing angle squared, which is actually the best constraint we have so far. Here it's for the tau flavor, from here it's for the muon flavor from collider searches. Now, this is a future experiment, so I'm talking about it before LHC because it's again an E plus E minus collider. FCCE is a future circular collider with a circumference of 90 kilometers. And in practice, it will be a Z factories. It will produce a very large number of Z bosons, and that will allow to strongly improve the limits on the active sterile mixing angles. So let me show you that. It's shown here, it's for the tau flavor, but it can constrain the mixing with all active flavors. You see that you can go down basically to U alpha n squared of the order of 10 to the minus 10, 10 to the minus 11. Okay? So that's if this experiment is built, which we don't know yet. Okay, so now let's move on to the collider that is currently running, which is the LHC, the Large Hadron Collider. So how are heavy neutral leptons produced at colliders? They are produced via Drell-Yan production. So in the mediated by a W boson, again off shell or on shell depending on the mass of the sterile neutrino. And basically this is going to give you a sterile neutrino and a charged lepton, and the sterile neutrino is then going to decay. The projection cross-section, like this one, is proportional to the active sterile mixing angle squared. And now there is something very interesting. If your heavy neutral lepton, as in practice we expect, is a Majorana neutrino, it can give rise to lepton number relating signature, which is same sign dileptons accompanied by jets and no missing transfer energy, because you don't have neutrinos produced in the decay. So again, it's Drell-Yan production of a charged lepton and the neutrino, and then the neutrino, because of its Majorana nature, can decay into a charged lepton of the same sign, as this one. So it's E plus or mu minus, for instance. And then the W decays to jets, okay, to have same sign D leptons. Now I'm presenting you updated constraints on heavy neutral leptons, which is taken from this paper. So the only thing I'm going to comment here, so the main goal of this paper was to see the constraint that the D-Neur detector can set, and basically it's given by the blue area here. So again, this is the mixing with the electron flavor, the mixing with the muon flavor, it's written here, this little box, and the mixing with the tau flavor. And they have added some new experiments that I'm not going to describe, but what I want to show here is the new constraint from LHC. So here, this is the CMS constraint. So you see that in the electron and muon flavor, we start approaching the same level as LEP, 10 to the minus 5 on the mixing angle squared, but now for larger masses in the several 10 GeV range. And again, so these limits are limited again by the same thing, that the production cross-section is proportional to the active sterile mixing angle squared. But you can do better than that if you look for displaced vertices. Displaced vertices means that when the two proton beams collide, you produce some particle that is long-lived and that decays away from the interaction point because it is long-lived. And actually, your sterile neutrino are particles that can be long-lived precisely if the active sterile mixing angles are small, because again, their decay width is proportional to the active sterile mixing angle squared. So this is again the mass of the sterile neutrino versus the mixing angle squared. And now we go to much smaller values, here 10 to the minus 7, 10 to the minus 8, 10 to the minus 9. And let's see what we can possibly, which region we can constrain by looking for displaced vertices at the LHC. So again, there is the price to pay, which is a small production cross-section. So there is a limit in red below which you cannot go because you will not produce enough N. And how comes that you can go so at the level of U10 to the minus 5 so low to such low values of the active sterile mixing angle? It's because there are very few long-lived particles in standard models, some B meson, but after some distance, you have practically no standard background. There's always a little bit of background, sometimes instrumental, but you have almost no standard background when you're looking for displaced vertices. Now you have these two lines in green and in blue. Where do they come from? So basically, you can probe this region here, the solid line. Where do they come from? So the decay rate is proportional to the mixing angle squared, but it also depends on the mass. When the mass increases, the decay rate increases. So if you go in that direction, so the mass increases, the decay rate increases, and at some point there is no the sterile neutrino is no longer long-lived. It decays promptly, so you won't see any displaced vertex. So that's why you cannot probe this region here to the right of this green line. And now the blue line is the opposite limit. So you decrease M, and it means that the decay width is decreasing, so the lifetime increases, and now the sterile neutrino decays outside the detector. So you don't see a displaced vertex. You have no sensitivity to again to that region, to to the left of this blue curve. So that's all I wanted to say about heavy neutral leptons. And then I have a next topic. How much time do I have? 10 minutes? Okay. So do you have questions so far? No? Okay. So let's move on to, oh, okay, sorry, it's just, yeah, okay. Again, it illustrates the same point. That's some estimates of the limit that you can reach with displaced vertices. Okay, so now I would like to talk about low-scale leptogenesis. So first of all, what is leptogenesis for those of you who do not know? So the idea is to generate the baryon asymmetry of the universe by first producing an asymmetry between leptons and antileptons. And for this, heavy Majorana neutrinos, like the one that you have in the seesaw mechanism, are very good. Because, first of all, you need, in fact, to generate a baryon asymmetry, the free Sakharov condition. So you need baryon number violation, C and CP violation, and a departure from thermal equilibrium. So here, in the case of leptogenesis, you trade baryon number violation by lepton number violation, and you use the fact that there are non-perturbative processes in the sound model, known as Faleron, that can convert an asymmetry in the lepton sector into an asymmetry in the baryon sector. So that's the idea of leptogenesis. How do you satisfy the third Sakharov constraint? So you need to depart from thermal equilibrium in order to generate an asymmetry. And the departure from equilibrium is going to be due to the expansion of the universe. So when the temperature of the universe drops below the heavy Majorana neutrino mass, they will decay out of equilibrium. And since they have their couplings to the lepton and Higgs doublets, these Yuka couplings here, in principle are complex. These decays can violate CP, and this provides the second Sakharov condition. So if they decay out of equilibrium and there is CP violation that makes the decay rate into leptons different from the decay rate into antileptons, you will produce a lepton asymmetry. And then it becomes a question of, you have to take into account that some processes can erase the lepton asymmetry that you have created. So you solve Boltzmann equation, you get a nice plot like this one, where you find some region where leptogenesis can work. This is called thermal leptogenesis with hierarchical neutrino masses, and basically you conclude that for leptogenesis to work, you need them to be, I didn't say that in the vertical axis, this is the sterile neutrino mass. So for leptogenesis to work, you need the lightest one to be heavier than roughly 10 to the 9 GeV. However, there is a way out if where you can go below that bound here. It is if instead of being hierarchical, the heavy Majorana neutrinos are degenerate in mass. In that case, you have an enhancement of the lepton asymmetry, and leptogenesis becomes possible for masses well below 10 to the 9 GeV. This is the so-called resonant leptogenesis. Yes? The different curves correspond to different initial conditions for your sterile neutrinos. So the red one corresponds to a zero initial abundance. So you assume that in the universe there is no other process that creates sterile neutrino than their inverse decay, meaning that it's a lepton plus a Higgs that produces a sterile neutrino. So thermal means that you assume that your initial condition is that the sterile neutrino N1 is in thermal equilibrium, okay? And finally, dominant means that you overproduce them by some process, like at the end of inflation in inflaton decay, you produce an abundance of sterile neutrino that is above the equilibrium abundance. And then you get different limits. So yeah, it's not really what I wanted to talk about. What I want to talk about is the possibility to realize leptogenesis now at low energy with heavy neutral leptons in the GV-TV range as we discussed previously. A first possibility is to do resonant leptogenesis with heavily degenerate heavy neutral leptons. I will not discuss it in detail, so this is a possibility that I've just mentioned. I will discuss another one in greater detail, which is a different mechanism which can work for heavy neutral leptons even in the GV range, and this is known as ARS leptogenesis for Akhmedov, Rubakov, and Smirnov. And in that case, the lepton asymmetry is created in sterile neutrino oscillations. So let me briefly describe how it works. So first you produce an asymmetry in the sterile neutrino sector through their CP violating oscillation, and this happens above the electroweak phase transitions, and then due to the interactions between the sterile neutrino and the standard model leptons, you redistribute the asymmetries that you have created in the different sterile neutrino flavors into the different active neutrino flavors. This is what is written here. And in the end, since you have also washout processes that violate lepton node, I forget to say that at this point, you have not created net total lepton asymmetry. You have created asymmetries in the different lepton flavors. But due to these washout processes that violate lepton node, you create total lepton number asymmetry. And then again, the sphalerons are going to convert this lepton asymmetry into a baryon asymmetry. I skip because, in the interest of time, I skip the technical details. Let me just say that you need for this mechanism to work, you need also some level of degeneracy, not necessarily as strong as the one indicated here. This is from some particular model that is called the new MSM. But you typically need some sort of degeneracy among the sterile neutrino. So what you can see here is as a function of the sterile neutrino mass and the active sterile mixing angle squared, you can see the region in green where low scale heterogenesis can work, and this color code indicates you the level of degeneracy. So it could even work for a degeneracy that is not so strong, of the order of 10 to the minus 1 or 10 to the minus 2. So how do we connect this with the previous discussion on heavy neutral leptons? Well, precisely, these sterile neutrinos that are involved in low-scale leptogenesis, in that case, leptogenesis through sterile neutrino oscillations, could be also searched for in the experiments that I've described previously. So what is shown in this plot that is due to these people is again on the horizontal axis the sterile neutrino mass, or an average of the sterile neutrino masses, the active sterile mixing angle squared on the vertical axis. The two black curves here correspond to delineate the region where leptogenesis is possible, so it is inside this region here. And here you have the various experiments we were talking about previously. So the dune near detector, SHIP, a beam dump experiment, FCCE. So you see that this parameter space where leptogenesis can work can also be probed experimentally. There are, of course, assumptions beyond those plots that I will not go into detail, but you need to choose to make some assumptions about the parameters. It's not completely for free. I mean, for leptogenesis to work, you need to assume some specific structure of your Yucca couplings between the sterile neutrino and the standard model lepton. So I think this concludes my lecture. So here what is that? Sorry, it's not the conclusion I wanted to. Sorry, the conclusion I wanted to show is that one, but it's a conclusion on leptogenesis, which you can read if you want. But basically, I said what I wanted to say. Thank you. Yes.
In the plot, in the previous slide, like you showed that M lightest equals to 0.1, which is the lightest gel neutrino? That one, M lightest.
Your question, sorry, because I couldn't
the
hear
mass, lightest mass.
No, because here in, as I said previously, I was very quick, sorry. So it was difficult to get all the information, but you always need some level of degeneracy between, let's say, N1 and N2. M1 and N2, the masses of the lightest two. Sorry?
Active neutrinos.
No. It's really the sterile neutrinos. Yeah. Because again, the way this mechanism works is through sterile neutrino oscillations. So sterile neutrino oscillations, which are I didn't enter all the details, but you could ask what drives this oscillation. So I can ask if you have I can answer if you have a question, but first you create an asymmetry in the sterile neutrino sector. So actually, most of the studies are done by assuming just two sterile neutrinos, N1 and N2, which are enough to generate the 2 delta square that you need for oscillations. So this M here is an average of M1 and N2, which are very close to each other. This is the level of degeneracy that is indicated by this color code. So M1 and M2 are very close of each other. Those are the masses. It's big M1 and big M2. Those are the masses of the sterile neutrinos N1 and N2. So that's the average mass.
So that NH normal hierarchy is for not active but sterile. That NH in your plot.
This M is for the sterile neutrinos.
Like NH there.
Sorry. The normal hierarchy is of course for the hierarchy of the active neutrinos.
Active neutrinos.
Yes.
But like that plot is how to say, like how much it's like depends on the active neutrino mass in this scenario.
How much it depends on the active neutrino mass? In fact, not that much. So you have a different plot for inverted ordering. But again, it's always the same story that you have more parameters in the seesaw mechanism than you can actually measure in neutrino oscillation experiments. So as I said, some of these additional parameters of the seesaw mechanism have been fixed to produce these plots. That's what I was saying previously. So there is indeed a dependence, but there is, if your question is, can we test, for instance, this mechanism by looking for CP violation in neutrino oscillations? The answer is in general no. But I should also mention a work that has been done by Pilar Hernandez and collaborators, where they tried precisely, by studying the ARS leptogenesis, they tried to see what you actually could constrain, which parameters you could constrain by requiring successful ARS leptogenesis. So you can actually say some things about the sterile neutrinos, about their mass difference, about certain CP violating phase. But there is no one-to-one correspondence between the CP violation that you need for leptogenesis to work and the one that you can measure in neutrino oscillation experiments.
Thank you very much.
Is the invert hierarchy different, largely different from this plot?
I think I don't remember very precisely. You have a different alloy region, but you still have an alloy region. So I don't think it's drastically different in the sense that you typically need the same level of active sterile mixing. And you get something similar to that. I don't remember exactly. I don't have it in my slides. I don't remember exactly how it is, but qualitatively, the answer is quite similar.
Just a curiosity. I noticed in one of the exclusion plots that you showed for heavy neutral leptons that among the curves there was one about dune prism. And I was wondering, yeah, probably this one. I was wondering why among all the near detectors that Dune is planning to have, why namely Dune prism appears in these plots.
So
what
prism,
was specific about prism in this case?
I mean, the authors of this study, who pick up that detector because it's a movable detector. So
Sorry?
It's a movable detector.
Yeah.
You can either locate it on the beam axis or off axis. And actually, I mean, it's written in very small here, but you have, as I said, the region that the prism can probe is within those blue curves. And actually, let me read just to be sure I remember correctly. So the dotted blue curve, I don't know if you can see. There is a solid blue curve. There is a dotted, maybe it's easier to see here. There is a solid one, there is a dotted one, and there is a dashed line. So the dotted blue curve corresponds to on-axis running of prism. The thin dashed blue curve corresponds to, okay, no, it's different. It's a background free analysis. So now the solid contour shows the sensitivity of Dune prism, assuming a given number of proton on target, of course, and an equal running time between on-axis position and 6 different off-axis locations. I'm just reading the text here. So that's the reason. The improvement doesn't seem to be spectacular by eye, but that's the reason why they considered prism in that study.
So I understand the claim is by moving the detector and using different flux configurations, they explore a bigger range.
Yeah.
On the other hand, probably by using prism and not a different detector which is bigger, they sacrifice on statistics. Anyway, yeah.
Yeah, probably. Then I don't know. So prism is liquid argon. The other ones are what? Maybe they are different.
At least what is supposed to be the big near detector that is being planned is also liquid argon.
Also liquid argon.
Yeah.
Okay.
Perhaps at the second stage there will be a gas argon.
Okay.
Anyway.
Okay. So yes. So unfortunately, I'm not able to give the motivation of the authors other than that one to move to locate prism at different off-axis locations. Yes.
Hello.
Hello.
So my question is, previously I have studied the case of right-handed neutrino leptogenesis, and it is different from right-handed neutrino oscillation induced leptogenesis. It happens through the decay of right-handed neutrino.
Yes.
Not through the oscillation of sterile right-handed neutrinos.
Okay. Sorry. To be sure, if I completely understand, can you repeat your question?
I'm asking that how it is different from right-handed neutrino decays that can induce leptogenesis.
So what are the difference? I mean, the mechanism beyond leptogenesis in the two cases are completely different. The common point, I would say, are the way you... Okay. Something I didn't say at all is that, first of all, in this mechanism, in the low-scale ARS mechanism, the sterile neutrinos are never in equilibrium. Okay, they are produced the same as can happen in standard leptogenesis. They are produced through inverse sterile neutrino decay, and they are never in equilibrium. So that's why you can easily produce an asymmetry in the sterile neutrino sector. And for that reason, people often call this scenario freezing by analogy with dark matter. They call it often freezing leptogenesis, while the leptogenesis from heavy sterile neutrino decay, they call it freeze-out leptogenesis, again by analogy with dark matter. So, that's the difference. What is the common point? The common point maybe is the role of the washout processes. So here in ARS leptogenesis, they play an important role because typically ARS leptogenesis will produce you an asymmetry between flavors, but a vanishing total lepton asymmetry. So these lepton violating washout processes are crucial
Yes.
To erase differently the different flavors and produce a net lepton asymmetry. Because oscillations by themselves do not violate lepton number.
Okay.
So I hope I answered the
Yes.
question. If not clear,
Yes, I got my answer.
to ask.
Thank you, sir.
You're welcome.
Okay, if there are no more questions, no more comments, okay, let us thank Stefan.